establish bridges with college, with the university. And that's what we had in mind for about a couple of years. And we are going to the point we have this consistent lecture series. So I thank you for your presence. And if you have any connection, if you are a school teacher or if you have any connection with school programs, please make sure you put us in contact with this program. I also would like to thank Professor and Dr. Michael Kaufman for accepting our invitation to come and talk to us about water in the universe. Dr. Kaufman is the chair of Physics and Astronomy Department at San Jose State University. Can you hear me?
Yeah.
Can you hear better now?
Yeah.
All right. So he's the chair of Physics and Astronomy Department at San Jose State University. He's a leading research in exactly the topic he's going to be presenting, water in the universe, and more particularly water found near sites of star formation. In previous lectures, we saw that stars are formed when gravity kicks in and then efficiently bring gas and dust to a point that becomes so hot that it becomes self-illuminating. And so this radiation interacts with material surrounding the star. And Dr. Kaufman, he works with computers trying to understand how these radiations pass through this gas and how the signature of molecules, specifically water and oxygen, is then brought to telescopes and then to computers, and then we model and analyze. So I will not take too much of your time, and time of Dr. Kaufman.
So I'm mic'd up here. I assume I can be here perfectly fine. Is that good? Okay. I'm not very used to wearing a lavalier, so I know people want to put it down. I'll keep it just the way it is. Well, thank you, Celso. What Celso didn't mention is we're old friends as well, which is it's really nice to see him. It's really nice to be visiting here. And Olenka Hubitsky is in the room too. She teaches for us as well as here at Evergreen. So it's nice to see some familiar faces. So I always like to start off talks on this subject by showing this painting, which has been hanging on the wall in several of the buildings at NASA Ames for 30, 40 years now. And it really nicely, for me, captures the kinds of problems that we're trying to answer in astrophysics, and in particular in the astrophysics that's trying to understand star formation, planet formation, and the eventual emergence of life in the universe. And if you take a look around this plot, you'll see a couple of things. I think the artist had in mind the formation of galaxies over here. Maybe these are some more distant galaxies in this part. Maybe a baby solar system with a planet forming around it. A molecular cloud, which I'll talk about in a little while, belching out some interesting chemical elements. Those elements forming into planets, some of it being carried on comets. And it's here nicely connected with the history of the Earth, which is portrayed sort of in a timeline going this way, going from a period of very active volcanism early on, and also very simple molecules down here on the bottom. The artist was trying to portray water molecules, and then simple molecules turning into something more complicated, and then strands of DNA, and maybe simple organisms. These things that look like muffins floating in the water, I'm not sure exactly what they are. Into more and more complex forms of life that finally crawls out of the water, turns into dinosaurs, primitive man, and then of course reaches the highest point in evolution, which is the astronomer. You're supposed to laugh there. But it's a nice portrayal of how we're up here on the mountaintop trying to figure out what happened back there to lead to this. And so water is the thing that's going to tie this talk together. But I need to give you some background information, and here are my goals for this talk. I want you to learn some basics of the interstellar medium. That's the fancy name that astronomers give to the stuff between the stars, and how that relates to star formation. I want you to become aware that there's this field called astrochemistry, where people study the chemical processes that go on in space, and how we can detect those various chemicals. I'm going to talk specifically about how we think water is made in space, and there are several ways, and it's a bit of a sort of 20-year-long story that I'll tell you about tonight. And hopefully, if you're interested, you'll be curious enough to go learn some more detail than I can give you here in tonight's talk. So, nice fisheye view of the night sky above some telescopes. Actually, I guess not. I think this is a star party. There's just some astronomer people down here. The Milky Way galaxy cutting across the middle. Some meteors coming in through the Earth's atmosphere. And there are even a couple of galaxies in this picture. So it nicely shows the scale of things that we're interested in astronomy, from the little bits of dust left over from the formation of the solar system coming through our own atmosphere, to the stars that make up our Milky Way, to things that are much, much more distant, but also have similar chemical elements and physical processes going on. If you take a cut across our own Milky Way galaxy, our home galaxy, in which the sun and the solar system live, what you notice is that it's arranged in a very flattened disk. This picture doesn't do justice to how much contrast there is between the thickness and the width of this, but just to give you an idea, this thing is about 100,000 light years across. That is, let's see if I do the math right, I think it's about 9 quadrillion miles. It would take light 100,000 years to go all the way across here. It's only about 1,000 light years across in this direction. And the vast majority of the stars, and also the star-making stuff, live in the flattened disk part of the Milky Way galaxy. This direction is the center of our galaxy. We live outside of there, about halfway out, so this is the view towards the center. A couple of common winter constellations, the constellation Orion and the constellation Taurus, are over here, a little bit out of the plane of the Milky Way. And you can see these dark lanes, which are not places where stars are missing, but instead places where dust grains, which make up a little tiny bit of interstellar space, but are big enough to block visible light, are preventing starlight from reaching you. Just to give you some numbers, there are something like 400 billion stars in our own Milky Way, which is just one of very many galaxies. If you were to weigh how much of the mass of the galaxy is in stars versus how much of it is in the stuff that's not stars, about 95% of it is locked up in stars, and about 5% is in gas with a little bit of other stuff. It's mostly hydrogen gas in a couple of forms, either atomic hydrogen or molecular hydrogen. And there's also this stuff that we call dust, which is just little tiny solid particles, mostly made out of things like what you would find in rocks on Earth, silicates. And those are the things, although there's not many of them, that are responsible for blocking the light. If you have a tube of gas, it usually doesn't block visible light, but if you've got a room full of chalk dust, it'll block the light really well. So think of this as chalk dust blocking your view. So that's the basic layout. And here's a nice close-up picture of part of the Milky Way. Again, beautiful dust lanes cutting across here. These are all stars. In fact, so many stars that it's very difficult in many cases to pick out the individual stars. Lots of dust blocking the way. And then there's this interesting reddish glow here. And that's the result of very massive stars giving off ultraviolet light and exciting hydrogen atoms, which are then giving off their own light in very specific colors. And the reason that we know this is that we can study the spectrum of that light. So here's a little spectroscopy lesson for those of you who need to brush up. This is a photograph of a gas tube that is filled with hydrogen gas. A high voltage has been passed through it, and it's causing the electrons to crash into the hydrogen atoms. Those hydrogen atoms move up to excited levels, to high energy states, and when they cascade back down, they give off a series of colors. And that pink, kind of electric pink glow that you see here and that you saw here is the result of the energy level spacing in hydrogen. And if you were to split up that light through a prism, you would find that that electric pink is a combination of a very distinctive red, a very distinctive kind of aqua color and a somewhat fainter blue thing right here. And that's the idea of taking light from an astronomical source and breaking it up into its constituent colors is the whole enterprise behind what we do in interstellar studies. We can't go out and fly to a star-forming region and scoop the stuff up and figure out what it's made of. We have to use the light that it's sending us and decode that light and figure out what's going on. I've got this light box up here, and I won't have time for everyone to come up and look at it. But it's a set of tubes. There's 3 different gases, and what you can see from this switched on is that the top gas has kind of a pale yellow color, the middle one has a very orange color, and the bottom one has a very blue color. Let's see, I need a volunteer. Who would like to volunteer? Okay, come up quick, come up quick. He's going to be our spectroscopist for a moment. He's going to put on these special glasses. These glasses are basically prism glasses. They have very, very fine lines etched in them. Go ahead and put those on. And then take a look at the light bulbs and tell us. No. What do you see?
I see the colors sort of like arranged together around the.
Okay. Can you describe them a little bit?
Yeah, there's like a red, and there's an orange, and yellow, and green.
Okay, which one is that for?
That's for the orange.
The orange one. Okay, so that orange light is made up of a bunch of different colors.
Yeah.
How about the yellow one on top?
The yellow one's yellow, green, and blue.
Okay, and the bottom one?
The bottom one is like a pale yellow, a green, and then like a dark violet.
Okay, does it look anything like these?
Yeah, it looks exactly like that.
Okay, good. So he's vouched for us that if you take the light from these 3 bulbs. Thank you very much, by the way. What's your name?
Yoshimar.
Yoshimar. Thank you very much. Let's give him a hand. So what he just described for you is the chemical fingerprints of these 3 different gases. The top one is helium, the middle one is neon, and the bottom one is mercury. Neon, by the way, is chosen for neon signs because it's got that nice distinctive catch your attention electric yellow or electric orange. Lots and lots of colors that will grab your attention and say, you know, hot coffee or whatever it happens to say. So that's the idea behind spectroscopy. If we can collect the light from a source and split it up into its constituent colors and compare it with a laboratory spectrum that we have of these gases, we can figure out what it is. And that's exactly what we do in astronomy. Now let me tell you a little bit more. It turns out that while atoms, like helium and mercury and neon, give off most of their light in the visible part of the spectrum, most more complicated things like molecules, where hydrogens are bonded together, or hydrogens and oxygens are bonded together, they tend to give off their light in parts of the spectrum that we can't see. And so we have to build devices to collect their light and split up their light and detect whether they're giving off light at different colors, if you will, just not colors that we can see. And most of what I'm going to talk about from now on will be infrared light and radio wavelength light outside your ability to see it, excuse me, but well within our capability of detecting. One more little detail I want to show you. Most of the time astronomers don't, is this thing feeding back? No? Most of the time astronomers don't display their spectra using pretty color bands like this. Usually they use graphs to do it. And the graph in the middle is the one that you should pay the most attention to. This is a graph of what wavelength of light we're talking about. So the blue end of the spectrum here, the red end of the spectrum here, nicely lined up with these. And the height of these lines represents how bright they are. So the bright red one gets a tall line, the somewhat fainter blue gets a shorter line, and the really pale blue over here gets a short line as well. Don't worry about this, just suffice it to say that there are other ways of detecting them, but this is the one I want you to pay attention to. So, what can we learn from the spectrum besides what the stuff is made of? Well, we can tell what atoms, molecules, and solids are present. We can also tell how much of them there is by comparing the relative brightnesses. So typically in interstellar space, we don't just have a blob of one gas. We have gases mixed together. And as a result, we get spectra that are mixes of those lines. And so you can take a look at a spectrum and say, ah, those 4 lines over there, they look like hydrogen, and these 3 look like helium, and these look like mercury. And by taking a look at the relative brightnesses of those, you can tell how much of each one there are. That's how we know that there's mostly hydrogen out there. You can also, in more detailed analysis, tell things like how hot the gas is, how dense the gas is. And by carefully looking at the spectra and with the right equipment, you can also tell whether the gas is moving away from you, moving towards you, rotating, or doing something in combination. So here's everyone's favorite horror, the periodic table, right? Everyone hates this, right? Yes? No? Okay, some of these guys love it. I love it. It's a beautiful thing, but the main reason that I love it is that astronomers don't have to deal with this complicated periodic table. Astronomers have this thing called the astronomer's periodic table, and the reason that we focus on this astronomer's version is that really all that we care about are the most abundant things in the universe. So as I mentioned earlier, hydrogen is the most abundant thing, and the size of this box represents about 90+% of all the sizes of the boxes that are here. Helium is about an 8% box, and then there are some pretty interesting atoms here: carbon, nitrogen, oxygen, and neon, and then magnesium, silicon, and sulfur, argon, and a little bit of iron. And I'll give you the 30-second summary of all astrochemistry right here. These 2 were made in the Big Bang. These were made in little stars. These were made in big stars. That's all you need to know. Okay. Done. You pass astronomy. And what's nice about this is that you can look at this diagram and say, I wonder what combinations these might find themselves in. And a real basic premise of chemistry is that you have something that's the limiting amount and something that's the infinite reservoir over here. And then you might have some limiting amounts down here that can mix with some infinite reservoirs here, or some even more infinite ones over here. Anyone want to call out some molecules you might be able to make from these simple combinations?
H2O.
Oh, H2O, good one. I wonder what made you think of that. So, okay. 2 of these and 1 of these, and you still got as many of these left over as you want. Anyone else?
Carbon dioxide.
Carbon monoxide?
Dioxide.
Dioxide, sure. You can put a carbon with an oxygen, or you can put a carbon with 2 oxygens, whatever you like. Anyone else?
Ethanol.
Ethanol, sure. So do you remember the formula for ethanol?
C2H5OH.
Yeah, okay, so did you hear what he said? A couple C's, a couple H's, a couple O's. Great. Easy to do. There's one other molecule that you probably didn't think of, but which stick out like a sore thumb here. Put 2 of these together, right? You can have as much of that stuff as you want. And there's still plenty left over to mix with these. So, just a guess. Interstellar space is going to have some hydrogen molecules, some water molecules, some CO molecules, some ethanol, whatever you happen to like. Here's a spectrum of a star-forming cloud taken with a space observatory called Herschel. And you know how I told you the height of the lines represents how bright things are, and you can have mixtures of spectra? So this is the spectrum of a gas cloud called the Orion Nebula. And every single one of these lines is a spectral line from some molecule. And take a look at the list here: methanol, hydrogen cyanide, sulfur dioxide, formal cations, dimethyl ether, water, carbon monoxide. Oh, look at that. Monoxide, but there's dioxide too. Methylformate, basically all things made out of simple combinations of the abundant elements. And using a computer program, you can separate these things out and figure out how much there are of various ones. There are people doing whole PhD theses on this spectrum right here. Here's the list. This table is only good as of about a year ago. There are a couple more things to add to the list. But this is, as of last fall, 194 molecules have been detected in space. And they range from the simplest one, H2, which you probably can't read right there. There are a couple things with aluminum and chlorine and so on. But the vast majorities of these are combinations of HCON, as you would expect. But there are some surprising ones like C60, C70, C80, carbon chain things that can even form in space, nice stable molecules. And here's a list of some of the things on there. So we know there's a really rich, interesting, important chemistry going on in interstellar space. And what I'm going to focus on for the most part, the rest of this talk, is just, where is H2O? Where are you hiding? Up. See, my eyes are bad. That's N2O.
Yeah.
There it is. It was hiding. It was discovered in 1969 using a radio telescope under very, very special circumstances. But we really didn't get good at detecting it until the last 15 years or so. And I'm going to tell you about some of those. So, real quick, conditions in here. Recognize this constellation?
Orion.
It's Orion, right? It'll be up around 11 o'clock tonight, and it'll be up all winter long for you to see in the nighttime sky. One of those things is not a star, it's the Orion Nebula, the thing I showed you the spectrum of a few minutes ago. And if you had infrared eyes, you could see the radiation coming from dust grains that were mixed in there. Remember that 1% dust that was really good at blocking light? Well, it takes the energy from the visible light and re-radiates it in the infrared, and you can see it with an infrared telescope. Tons and tons of this stuff. If you zoom in to the nebula, here's a very modern, earlier this year, large telescope view of the Orion Nebula, and you can see there's this beautiful mixture of swirls and patterns and bubbles, and there are jets and outflows and all kinds of interesting things going on here. A couple of details about its conditions, just to give you some reference. It's essentially all molecular hydrogen, 99+% of the molecules are molecular hydrogen. The dust in there plays an important role because starlight can actually break hydrogen molecules apart, so you wouldn't have them if the dust wasn't there to block the light. Most of the cloud has a temperature of only about 10 degrees Kelvin, so 10 degrees above absolute zero, very, very, very cold conditions. And the density of material in here is incredibly low. It's hard to imagine what this means. Just to give you a sense of the difference between this, anyone know how many atoms or molecules of water there are in a gram of water? Probably don't know it off the top of your head. It doesn't matter. It's about 20 orders of magnitude greater than this. So, in order to take this raw material, which has a lot of material in it, you need to compress stuff over an enormous volume. And the process of star formation is taking this very, very diffuse stuff and cramming it into a space where it's dense enough for, as Celso mentioned, for hydrogen fusion to begin in a star. So here's the cartoon version of star formation. This is an updated version of a plot that was shown to me when I was in graduate school. And it was largely the case when I was in graduate school that none of these things have been observed directly. They have been inferred from spectra. But the condition has changed a lot since then. And I just want to point out three things on here. It's really this one, and this one. These are a blob of interstellar cloud that's going to collapse to form a star. The main distinguishing characteristic here is that there are some places where it's a little bit denser than its surroundings, embedded in a more diffuse cloud. There's this phase here called the protostar phase, where material is falling onto a star, but there are also fast-moving jets and outflows coming out from the star. And then there's this phase down here where a disk is formed around the equator of the star, but that disk is not yet formed into planets. And I'm going to show you some images of these things as they really look in observations that are much more recent. So let's take a look first at this thing that we call a prestellar core. It's basically a blob of gas, trillion miles across, in which, rather than being completely uniform, the gas has built up in some places and become more diffuse in others. And maybe that's because of motions of material inside the cloud. Maybe it's because it crashed into another cloud and compressed parts of it. We don't really know all the details, but this is the state that we think star-forming clouds are in just before they begin to form stars, just before gravity starts to take over and accumulate lots and lots of material. So why do you think this is dark? Any guesses? Someone started to say something.
Dust.
What's that? Yeah, it's the dust, right? This is a blob of interstellar gas. It's got about 1% dust in it, and that dust is preventing you from seeing the stars that are behind this cloud shining through it. If you use a detector that can see infrared light, it turns out infrared light can get around that dust. It's got a longer wavelength than visible light, and so if you use an infrared camera, it looks a little bit different. You can actually see through it a little bit. You can tell there's stuff here. It's dimmer than it would be if it was transparent. And you can also tell that there are some places in the center where you don't see any stars at all. And that's where we think these condensations have started to form. So soon after this, gravity is going to start pulling material in faster and faster and faster to form a star at the center. So this is as pre-stellar as we think we can get. It's just on the verge of becoming a star. So cartoon, real deal. There's also this outflow phase. The physics is still not completely understood, but at the same time the material is being pulled in gravitationally toward a star. Some fraction of the material also gets shot out in these very fast supersonic jets that eventually clear away the surrounding cloud. And these Hubble Space Telescope images show two blobs in star-forming clouds where the star that's buried inside of here is pushing material outwards in these bipolar outflows. So you can see a shock wave right here where Mach 10 gas is crashing into the interstellar medium. Same thing here. I think I have a close-up of one of them. Yeah, so there's a baby star inside here, and there's a jet coming out this way, a jet coming out this way. You can see blobs in here, which may indicate that it's an episodic process rather than a smooth process. But cartoon version, the real deal, except this is rotated about 90 degrees from the real deal. What about protostellar disks? These things that form around the equators of stars. It's a consequence of the conservation of angular momentum. That material can't fall directly onto the star. It has to spiral inwards through a disk. And so we think this is a ubiquitous feature of baby stars. In these four pictures, you are seeing young stars against a bright background. And once again, the dust in that disk material is blocking the background light from getting to you. So they're in silhouette. Baby star, baby star, baby star, baby star, somewhat further along in the process because it's cleared away the material around it. But there's a disk of potentially planet-forming material around its equator. And the most recent and probably most incredible view of a protostellar disk is this view from a new telescope called ALMA. This is an image taken at radio wavelengths that are given off by very, very cold dust grains. So you're not seeing the bulk of the disk, you're seeing the dust that's in the disk, and those little solid particles appear to be missing in certain locations. Just to give you a sense of scale, this oval right here is around the size of our solar system. Neptune's orbit would fit right in there. So this stuff out here is significantly further out than the material in our solar system. But to me, this is just a stunning view. The idea that you could have a young star with a disk around it and see this level of detail inside of it. These clearings may indicate either that there's an object here that's sweeping out material or that there's an object further in that has an orbital resonance with this stuff and is clearing it out on repeated regular passes. So let's get back to water, which is the reason we're here. Why should you care about it? A couple of details. As I hope I've convinced you, it should be one of the things that is made out of those common elements, hydrogen and oxygen. In fact, it should be the most common thing that's made out of hydrogen and oxygen, since it's a combination of the most abundant and the next most abundant thing. And by studying the spectrum of water, we can figure out the physics of these star-forming regions. It's potentially very important for allowing these clouds to collapse in the first place, and I'll say a minute about something about that. It is an important building block for planets. I'll show you some of that. And as we all know here in this room, it appears that you need water for life, at least all the life that we know about. I'm going to go through this very quickly and just say that the spectrum that water gives off is potentially much more energetic than some of the other common things that you can make. And as a result, if you're trying to get a cloud to collapse on itself, it's really good if you're able to shed some of the heat from that collapse. And water is really, really good at doing that. That's all I want to say. So, when I started studying water, there were essentially two chemical routes known for making water. And this is probably the most, I don't know, maybe the most complicated, maybe the second most complicated slide in the presentation. But these two routes were known as the low temperature and the high temperature route. And they both start with oxygen mixing with hydrogen or an ion that forms from hydrogen. The low temperature route is the one that happens in gas that's 10 degrees Kelvin. Without going into too much detail, there are these high energy particles in space that come, they crash into the molecules in the cloud and ionize some of the hydrogen, which kicks off a set of ion reactions. You'll notice an ion mixes with another hydrogen, makes another ion, mixes with another hydrogen, makes another ion, and an electron comes along and you end up with water. So this is what's known as the low temperature or the ion neutral route. The other route is this one that's a high temperature route, and you'll notice that it doesn't involve any ions. It's just oxygen combining with a molecular hydrogen to make this radical called OH, and then very quickly combining again with another hydrogen molecule to make water. And you would expect in interstellar clouds that the dominant version of these reactions would be this one, just because the temperatures are so low. Now, my early research was on trying to understand this route. And the reason that we focused on this route is that the tools that we had to detect water 20 years ago or so were not particularly good at finding the water that went this way. And I'm going to show you some details about this fast route first. So here is a close-up showing an image of light coming from hydrogen molecules in an outflow from a star in the Orion Nebula. The newly formed star is down here, and each of these little blobs that you see moving out, if you sort of squint your eyes, you can see there's a lobe here and a lobe here, and that's supposed to be like these two lobes right there. And we know from the spectra of this hydrogen that it's dense, about 1 million particles per cubic centimeter, dense for an interstellar cloud. And we also know that its temperature is about 2,000 degrees. Not 10 degrees, but 2,000 degrees. And the interpretation of this was that the fast-moving material coming out of this newly formed star was crashing into the surrounding cloud and creating what we call shock waves. So in this particular case, the material is coming out at about 40 kilometers per second, which in these clouds is about Mach 40. So this is highly, highly supersonic material, and when it crashes into its surroundings, the energy motion, the kinetic energy, gets converted into thermal energy. And that thermal energy is then radiated away by the hydrogen molecules. Now what's cool about this is that we know that high temperature route for water. If you take oxygen and hydrogen and you heat them up to temperatures of 400 or more degrees, you make this reaction go, and I got chopped off a little bit here, I apologize, but this should be OH, oh that's right, OH plus H, and then that OH combines with another molecular hydrogen to make water and another H. And the prediction for the models that tell us what's going on in these shock waves say that if you have any oxygen around at all of it should get converted into water, 100%. It's incredibly efficient and incredibly fast. So I built a computer model to take into account all the physics that I thought was going on in this cloud. So the quantum mechanics of the individual molecules, how radiation leaks out of the cloud, the chemical reactions, what the dust grains do, how the dust grains wrap around magnetic fields, the fluid dynamics of the shock, how energetic particles ionize the gas, and so on. And the end result of that is a graph that looks like this that tells you how the temperature changes, how the chemistry changes, and so on. And the only thing for you to notice here is that when the temperature goes up, the amount of water goes way up. That's all. If you've got oxygen, you make lots of water. Simple prediction. And this is a computational spectrum, a spectrum that I produced in that computer model to predict what the spectrum of water would be like. So remember those lines we saw 15 minutes ago? This is another one of those graphs of wavelength versus brightness for a whole bunch of lines of water. And also for CO and also for H2 and so on. The only problem is that you can't detect any of this stuff from an observatory on the ground. Anyone have a guess why that might be? Yeah.
Dust in the atmosphere?
It's not dust in the atmosphere. It's something else. I mean, it's true that dust in the atmosphere would block, if you had a really dusty cloud go over your observatory, you wouldn't be able to see this stuff. Someone said, okay, so first he said air, which could be really, really dry, but water vapor, yeah, water vapor in the atmosphere is the main reason why you can't detect this on the ground. So you can have a water molecule 1,000 light years away in space, radiate a photon that comes all the way to Earth, and in the last 60 miles, it gets absorbed by water molecules in our atmosphere. We're left sitting on the ground wondering what happened to it. Right? So if you want to detect water from space, what do you think you have to do?
Detector in space.
Yeah, you need to put an observatory in space. And so when I was finishing my thesis, that's when the first of these potentially water detecting telescopes was launched. It had the very, very fancy name, the Infrared Space Observatory. Don't worry about the details of this. Suffice it to say that it was a relatively small telescope that allowed us to first start learning about what was going on with water in space. And here is a more modern view of that outflow region that I was telling you about. Here's that up to the right lobe and down to the left lobe where the baby star is here in the middle. And the telescope was small enough that its field of view was pretty huge. A single telescope pixel covered a region about like this. But we focused on this outflow because it was the most energetic, most obvious place to look for water formation that we could think of. And what I'm trying to show here is that you take the light from that, you pass it through those glasses, just like the guy was wearing up here before, and you get a spectrum out. And this spectrum is actually chopped into little pieces. We didn't detect every single one of those water lines, but we detected 8 of them. And by comparing the relative brightnesses of them to one another, and also by comparing the brightnesses to the brightnesses of the hydrogen that had already been detected, we were able to determine that, in fact, in this region, all of the oxygen that was available in the cloud was turned into water. It was a confirmation of that chemical prediction. Don't worry about the analysis. Suffice it to say that these things were as bright as we expected them to be and in the right ratios. So that was about all we could do with that particular telescope. Other fainter, smaller, less energetic regions of star formation were not particularly good targets for this kind of experiment. Now, soon thereafter, there was a small NASA satellite called the Submillimeter Wave Astronomy Satellite, and it also had a big, wide field of view, not particularly good for zooming in on particular locations, but its job was to measure the water content in not an individual star-forming region, but in big clouds. And so it pointed itself towards regions where we would expect the cold chemistry to be the dominant chemistry that was going on. And the expectation of the cold chemistry, and I guess I typed this wrong, is that about 1 out of every 100 oxygens would be in water in the clouds at large. So we pointed this thing at dozens of star-forming regions. Here's a list of them here. And don't worry about the numbers. Suffice it to say that what we found was that only about 1 in 10,000 oxygen atoms was in the gas in these star-forming clouds. So that taught us something about the chemistry. The chemistry was not doing what we expected it to do. If you just let the cloud sit there for a long time, bombarded by these energetic particles, it should make about 1 in 100. So something else must have been going on. And we came up with a model that takes into account what happens when gas atoms interact with dust grains. Dust grains are small. There are not that many of them, but it turns out they have a lot of surface area, and they turn out to be great catalytic sites for the formation of water. So the basic idea is this. You get oxygens and hydrogens to stick to the surfaces of cold dust grains, and when other hydrogens come along, they bond with the oxygen, make water, and you can even have starlight come along and knock some of these off back into the gas phase. So the prediction of this particular model is that you get about 1 in 10,000 oxygens returned to the gas, and 99.999% of the oxygen is water, but it's frozen on the grains. Not a place where we could look with this particular satellite. Here's a nice animation that someone made. Let me see if I can get it to start correctly. Showing a zoom into a molecular cloud, a couple of light years across, in which there's a bunch of star-forming regions. Oh, and what a scale jump. We go from 2 light years to 1/10 of a micron. And here we are on the surface of a dust grain, and there are hydrogens and oxygens hitting the surface. Sometimes they hit the surface and jump off. Sometimes they form molecules like molecular oxygen and go jumping off the surface. But if you build up enough of this material on the dust grain, basically enough to make a single layer on the dust grain, then you can hide essentially that 99.999% of the water on the surface. So we'll give it a few more seconds here to do its thing up. It's starting to speed up. Get all those molecules jumping around. And if you zoom out, what it'll look like is a thin layer of ice on the surface of the dust grain. So this particular model predicts that all of the oxygen is in water molecules. It's just that those water molecules are frozen to the surfaces, not in the gas. And this is just a chemical model that shows this. Don't worry about it. The main thing to see is this is all the oxygen in water ice, and there's just a little tiny bit of water gas that results from popping off of there. So, in 2009, a new and more advanced mission to study water and other types of interesting molecules in space was launched by the European Space Agency. It lasted for about 5 years. The main reason that it didn't last longer is that it's cooled by liquid helium, and liquid helium can't be perfectly contained. It eventually leaks out of the spacecraft. And once the spacecraft warms up, it's no good at detecting these very, very cold regions. It was a much larger telescope than the one that we had used before, where we just had the spectrum of that 1 pixel on the sky. It was very high sensitivity, and studying water is one of its main goals. And these are 3 key projects, big observing programs with the telescope: water in star-forming regions, Herschel observations of extraordinary sources, and the Herschel Oxygen Project, which were all aimed at trying to track down where all the oxygen was in star-forming clouds. You can tell that it was a very, very important mission because it made it to the whiteboard of the Big Bang Theory. Herschel and water were both mentioned there, so it must be important, right? And we looked for water in several different places. So the first place that we looked for it was in the cold clouds that hadn't yet formed stars. And to date, this is the single detection of water in one of those regions. So the dust grain chemistry seems to be working here. There are, based on the strength of this spectrum, we can tell that there are about 10 Earth oceans worth of water in the gas phase in this star-forming cloud, actually pre-star-forming cloud. If you assume that that water came from the frozen water popping off into the gas phase, then there's about a factor of 100,000 times more in ice, and that turns out to be about 1 million oceans worth of water ice inside this cloud. Now, that's still a small relative fraction of the total mass of the cloud. It's still mostly hydrogen molecules, but that's a pretty astounding amount of water for just this little blobby thing you see in the sky. We also looked in more detail at water formation in these outflow shock waves. Here is a visible light image of a star-forming dusty cloud. Here is a zoomed-in dust image showing a bipolar outflow, so gas moving this way and this way away from a newly formed star. And here is what we can do now with Herschel, or what we were able to do with Herschel. This is a map of the outflow. In the old case, all we got was a single spectral line, and we said, oh, there's water present. Now we can actually map it out. So here is a picture of what this outflow looks like if you have eyes that can detect water molecules. And so this is a more thorough confirmation that water is being formed in the places where outflowing material crashes into the surrounding cloud. The highest water intensities are these places where you see this thing kink and change directions along the way. There's also, by the way, water down at the protostar itself, but not something that we're going to talk about here today. Water is detected in literally every young star that we look at. Any star that has an outflow has lots of water. This is just a little mixture of different sources that you can see. The wide part here is the fast-moving gas. So this is gas that's moving at 30 or 40 kilometers per second. We can tell that from the spectrum. And then these dips in the middle are from cold water that's up closer to the protostar. And one of the questions that we're still trying to answer is, when you make the water in these outflows, is it then available to allow the next generation of stars to collapse on itself? And then we also detected water in one of those disks, one of those places where the star had already collapsed. It still had a disk around its equator. And here's the spectral profile of water. This has only been detected in 2 sources because this is a very small object with a very low water abundance, and it's just a difficult experiment to do. But this is telling us that there is lots of frozen water in this disk, and a little bit of it is out in the gas phase because it's being knocked off by stellar photons. We think that this is indicative of the kind of material that you would need to make something like the Kuiper Belt or the Oort cloud, the places where there are icy water ice bodies further out in the solar system. Here's a little animation. Let's see if I can get this to start again. I think I have to go back over. An animation of what people who study the formation of solar systems think is happening down in the protostellar disk. So this is going to be a zoom in. I think we get some music with this one. Yeah. Zooming into a protostellar disk, so baby star with that silhouette of dusty, gassy stuff around it. And as we get closer and closer, you see individual dust grains covered with water ice. And they start sticking together because water is nice and sticky. Nice polar molecule that likes to stick things together. And this might be the process by which you start the embryos that become planets in a protostellar disk. So to follow on from this, you can imagine going from these little clumps to what we call planetesimals, little oblong objects held together by molecular forces, which then collide to make small planets and then maybe big planets. These might be the embryos from which planets form. So water seems to have an important role in the sticking together of this stuff early on. Just to summarize the results that we had from Herschel, we detected water in a prestellar core, a place that's about to collapse, and that's this little blip right here. We confirmed the chemical prediction that outflows are really good at making water. They're really bright and energetic, although they're a relatively short-lived phase in the life of a star. They're good water factories. And then maybe some of this water freezes to the surface of the dust grains that we find in these disks that we think are going to produce the embryos from which we produce planets. Okay, just a little bit about things that are in progress or upcoming. As I mentioned, there were only 2 protoplanetary disks where we've discovered water. And what we'd like to do is get a much more thorough census of what's happening with that water and get it on many, many more objects. Just last month, NASA approved the production of a new spectrometer, a new device that's able to collect light from space and split it up into its constituent colors, that's designed specifically to detect the water that's on the surface of one of these protostellar disks. And this is a more complicated cross-section through a disk, but the idea is that you have frozen water on the inside and then a surface layer here with gas phase water. And this spectrometer is going to fly on this telescope called the SOFIA Observatory. It's a NASA airplane that has a Hubble Space Telescope sized mirror in it, and it's designed to fly up above the Earth's water vapor precisely so that you don't get blocked by that the water that's in the upper atmosphere. So it's going to have a spectrograph that can detect gas phase water here, and then also some related things like atomic oxygen and Hg, which is just an isotope of molecular hydrogen. And it'll be able to do this for hundreds and hundreds of disks. So we'll get a much better picture of how important water is in disks in general. I also promised in my abstract to talk about water at large distances. We're using a new tool now called the Atacama Large Millimeter Array, which is a radio telescope, not made out of a single dish, but made out of 66 individual radio dishes that are arrayed on this high plateau in the Atacama Desert in Chile, up at 16,000 feet. And the reason it's at 16,000 feet is, again, you want to get up above as much of the water in the Earth's atmosphere as possible. It's a nice bone-dry, steady temperature desert location. Really, really hard to work there at 16,000 feet. They have to do all kinds of special things to allow workers to work up here. And astronomers actually don't sit up here at the telescope. There's a control center that's a few thousand feet below that because you want your senses about you when you're working on this stuff. And what's cool about this telescope is that the individual dishes act as one telescope. So you can spread them out all over this plateau and detect really, really small details of nearby things. And the fact that there are so many dishes means that you're collecting lots and lots of light, even from distant sources. And we can see objects and take spectra of them coming from huge distances. So here's just an example. This is a map of a galaxy that's called the Spiderweb Galaxy. It's a galaxy that we're seeing now as it was about 10 billion years ago. So the Atacama Large Millimeter Array is capable of detecting these very, very faint sources. And the spectral line you see here and the spectral line you see here are emission from water molecules in that galaxy. So even 10 billion years ago, enough oxygen had been produced in the universe that it's capable of making water. And what we think is going on is that the galaxy core is down here. The galaxy is in a very early phase of its life during which lots of material is being fed onto a black hole at its center, and that black hole is shooting out radio jets. Those radio jets are much, much larger than the jets that we were looking at coming from these baby stars, and when the jets collide with the intergalactic medium, which must have some hydrogen and oxygen in it, it produces high quantities of water. So we think the physics that's going on here is very similar to the physics that's going on in protostellar outflows, except now we're talking about seeing it on a galaxy-wide scale instead of on an individual star scale. So, good. A couple of conclusions. Interstellar clouds contain the raw materials to make new stars. Water appears to play an important role in its energetics. Outflows are really good water factories, and the surfaces of dust grains are the places where most water is hiding out. We're getting progressively more sophisticated observations that are confirming our chemical models, and the next generation of instruments will give us the ability to take a real census, not just of the exceptional objects, but of objects across the energy and age range to see how water plays into the whole thing. Now, Let's see, I'll put that up when we get to questions. The one thing that I didn't talk about in great detail is how the water got here on Earth. It turns out that the Earth is in a location in the solar system where it's not particularly good at holding on to water, at least in the early solar system. It was too warm here, and so water would have been, it would have been frozen further out, and it would have been destroyed by the starlight closer in. So we think the water that we have here on Earth, and I won't go into detail about this, was probably delivered by icy leftovers from that protoplanetary disk when the sun was forming. Comets and similar objects crashing into the Earth after the Earth formed deposited the relatively small amount of water that we have here on Earth. So with that, I will wrap it up, and I'll show this cartoon, which is kind of snarky, but since we're talking about star stuff and its importance to us, I thought I'd just throw this up, and then I'll open it up for questions. So, I assume we have time for questions.
Yes, you indicated that water can be formed by two methods, the cold and the hot.
Right.
Okay, so ice exists. I'm trying to envision what form water is in the hot formation. I mean, in our atmosphere, it's a vapor.
Right.
Can a vapor exist in
Yeah,
space?
it's a vapor there too. So the phase that it can't exist in an interstellar cloud is liquid phase. The density is too low, and so you go directly on the phase diagram from ice to gas with no intermediate liquid phase. It does what's called sublimating. And that can happen either because the dust grain is warm enough for the water to pop off, or it can happen because an energetic photon comes along and knocks it off of the grain surface. Thank you. Go ahead.
You said the interstellar medium was the stuff in between stars.
Mm-hmm.
What exactly is the stuff?
Well, it's that stuff I was talking about. It's the hydrogen,
Just like gas.
oxygen. It's gas with a little bit of dust mixed in. But that stuff is capable of being formed into stars later on. So, and another thing I should mention, and those of you who are taking astronomy may know this already, but in addition to stars being formed, they also die. When they die, they spit stuff back out into the interstellar medium. So the interstellar medium isn't just this reservoir that's there to begin with and all gets used up. When low-mass stars die, they shed their atmospheres. And when high-mass stars die, they blow themselves to pieces back into the interstellar medium. And then the next generation of stars can form from that. In fact, one interesting point I should mention, the very first generation of stars didn't have oxygen and carbon and nitrogen in those clouds. It was probably just hydrogen and helium. So the chance that they actually formed planets is very, very small. You can't form planets out of hydrogen gas, at least not straight out of hydrogen gas. So we live around a star that's made from material that had been through multiple generations of other stars before it formed the sun. And that's why we're standing here.
Is it possible that they can regenerate over time, like in 10 or 15 years that we can see?
That what can regenerate? I'm not sure I understand the question.
You were explaining how stars, stars, they over time change.
Yeah.
I was wondering if they can regenerate, like they can, instead of growing, they can be able to multiply.
So I think correct me if I'm wrong, I think what you're asking is can one star turn into multiple stars?
Yes.
Is that right?
Yes.
Okay, so here's what we think is going on. When you take a look at a molecular cloud like the Orion molecular cloud, it's got something like 100,000 stars worth of interstellar medium in there. And that interstellar medium is not the result of one star belching stuff back out into space. It's the result of many stars doing that. And so in a way, when you form a new star out of that, you're incorporating lots of other stars into it. So it's not so much that you turn one into many, it's that you turn many into one. I don't know if that is sufficient or not.
How abundant is liquid water in the solar system, in our solar system?
Liquid water. So liquid water. Okay. So the main place where we know about liquid water is here on Earth. The water on Earth is highly abundant compared to hydrogen on Earth, and that's because the Earth has almost no hydrogen in it. Okay? It has molecules that contain hydrogen, but the most abundant element in the Earth is actually oxygen, and that oxygen is incorporated into silicates, which make up the rock, which is what the Earth is made of. The water on Earth, however, is a very small fraction of the mass of the Earth. You could evaporate it all away, and the Earth wouldn't care all that much. Let's see, the mass of the oceans is about 10 to the 21 grams. Is that right? 10 to the 24 grams, 10 to the 21 kilograms. So it's about a part in 10 to the 5 of the mass of the Earth. 1/100,000th the mass of the Earth. So it's relatively low abundance compared to the rock on Earth. It's relatively high abundance compared to the stores of hydrogen that we have. But you could take the Earth and all its rock and all its water and drop it into the sun, and the solar system wouldn't care.
And all this water came from outer space? All this water came?
Yeah, everything on Earth, whether it was incorporated into the Earth when the Earth first had silicate stuck together, or whether it was delivered by comets afterwards, it all was formed in space
So
before the Earth existed.
It wasn't trapped under...
Well, some of it might have been trapped, but it would have been trapped in hydrated molecules or hydrated minerals in the dust grains, which stuck together.
Thank you.
Can I ask a question?
Sure. Do I have to answer?
There's water and discovered in, well, we think there's water on Europa.
Mhm.
There's water on
Look,
Enceladus.
we know there's frozen water in both of those places.
Right. And we're suspecting there's liquid water on the
Right.
surface of Europa.
Right.
Was the stuff and there's much more percentage-wise.
Right.
How?
How is it much more percentage-wise?
Yeah, why?
Okay, so the really simple answer is that when the solar system was forming, it was warm in close, and that's why the only solids you have are silicates. And it was colder further out, which is why you had icy solids as well. And so if you look at the composition of a moon of Jupiter or a moon of Saturn, they have a much higher water to rock ratio than something like the moon or the Earth. And so oxygen's more abundant than silicates, or than silicon. And so if you stick stuff together out in the distant solar system, it's got a higher water content. I think the most recent model that I saw said that Europa, if its water content is as high as we think it is, Europa has twice the water that the Earth does.
Yeah.
Yeah.
Can you speak at this time to the abundance of water throughout planetary systems in the galaxy, or do you have any information? Yes.
So the two places that we have some handle on it are in those protoplanetary disks around two stars. And there we think what we're seeing is a little bit of water vapor that gets knocked off of much more abundant solid water that's on the dust grains. However, we don't have any direct measurements of water in fully formed planetary systems. So we see it in a couple of disks that have not yet turned into planets, but we don't have any information on the water content in ones that have converted that disk completely into planets.
Any wild speculation?
The wild speculation would be that it's just like it is in those disks, that it's a part in 10 to the 4, which is the ratio of hydrogen to oxygen.
I have a question.
Yeah.
So basically, water is some stuff very abundant everywhere we look, and so usually water is associated with life, or life is associated with water. Could you explore this idea?
Sure. So let me fall back on something else that has come a long way since I first learned about it, or since I was a first student. Many of you are probably familiar with this thing called the Drake equation, which is this equation that sets out a bunch of parameters that tell you something about the likelihood that there's life elsewhere in our galaxy. And those parameters include things like how likely is it that a star that forms will have planets around it. 20 years ago, question mark. Now, 100%. Okay? How likely is it that a star that forms planets has a planet that's the right distance away from its star to allow liquid water to exist on its surface? 20 years ago, question mark. Now, 50%, something like that. And given the fact that water is such an easy thing for the interstellar medium to make, just because it's so the raw materials are so abundant, I would say that if you have a planet the right distance and you have liquid water, I didn't talk a lot about it, but those other molecules that I listed are also interesting precursors to biology, for DNA and things like that. I would say the chances are very good. I sort of veered off from your question, but I think that captures it pretty well.
The silicate that makes up our Earth,
Uh-huh.
and you said that also makes up the dust in
Yeah,
there
yeah,
and
that's
everything.
right.
How does that dust form?
Good question. That's a really good question. So I didn't mention it, but we also know about these transitional molecules that are sort of bigger than what you normally think of as molecules, but smaller than the dust grains. They're these carbon chain molecules called polycyclic hydrocarbons. And they're basically hydrogen and carbon, as their name implies. They're stable structures that can exist in the environments around energetic stars. And we think they stick together. So you go from atoms to molecules, molecules to bigger molecules, and eventually those molecules get big enough that you form something that you would call dust. I don't know if that, but we have lots of evidence for those kind of intermediate sized molecules that we know from laboratory experiments if you stick them together and make what you would think of as a little dust grain.
It just looks like dust.
Yeah, it looks like a fluffy bit of rock.
So you mentioned in Chile there are the 66 satellite things. How does that distance on just a plateau of Earth affect the results that far away?
Okay, so there are two important things about telescopes, or two important design parameters about telescopes. One is how much radiation can it detect? And that's essentially determined by the size of the telescope. So the distance from, it's the collecting area of the telescope. If you think about, suppose you had a watering can, and you were trying to catch as much water as possible. The best way to do it is to have as big a bucket as possible, right? If you have a shot glass and someone pours a watering can over it, you're going to miss a lot of it. But if you have lots and lots of shot glasses or you have a big bucket, you'll catch a lot of it. And the idea behind having 66 dishes is to have as much collecting area as possible. The other important design criteria for a telescope is how far apart the two farthest parts of it are. And so when someone talks about well, so the Hubble Space Telescope is a 2.5 meter, roughly 10-foot wide telescope. So the most distant 2 points on that mirror are about 10 feet apart. For telescopes, sort of state-of-the-art telescopes on the ground, that's more like 10 meters. You can just build bigger telescopes here. And the ability to detect fine details is determined by that largest distance. So what they do with those 66 telescopes, if they want to see very, very fine details of an object, is put them as far apart as possible. And that gives them that fine resolving power, that ability to see small details. It turns out that it doesn't work that well unless your source is quite bright. So for some circumstances, you can't do that, and so you have to keep it in a more compact configuration.
And then actually one more.
Yeah.
You said, or you kind of kept mentioning, it's what scientists like think is happening. What needs to be discovered or found out that it becomes like fact, or you know what's happening?
Wow. Okay. So I was probably using think in a slightly different way than you're referring to it. What I meant was we try to construct the clearest explanation that we have for what chemistry is going on. The main thing that we do in astronomy is we find examples of something, and based on one or two examples, we speculate about what chemical processes or what star-forming processes are going on. And then we go and we try to find as many other examples of that as possible. So finding more examples and creating a coherent story that goes across many objects is really the key to saying something is true.
That's basically what they're trying to do.
Yeah.
Okay.
Yeah.
Thank you.
So would it be possible to utilize the spectroscopy technique to an exoplanet to find a biosignature?
In principle, yes. Technically, it's quite difficult. And the main reason it's so difficult is that at the distances away that exoplanets are located, even to the largest telescopes, the star and the planet are extremely close together on the sky. And so if you take a telescope and you collect the combined light of the star and the planet's spectrum is badly washed out. And so some of the telescopes that are being designed right now are trying to use clever techniques to block out the starlight and collect the planetary light without it being basically washed out by the star. But in principle, you could do it. In practice, it's quite hard technically. But there are people working on designs that'll be around in a decade or so that will be able to do it. And one of the things they'd like to look for is oxygen, water, things like that.
You mentioned that since water is essential for life, and there's water in many places, the fact that it's possible to get life somewhere else.
Mm-hmm.
However, organic compounds like sugars and amino acids, they show optical rotation, either dextro or levo.
Mm-hmm.
While chemicals within the laboratory, they have equal amounts.
Mm-hmm.
All organic compounds so far out of space do not show that optical activity.
So there's a very recent result using the ALMA telescope that discovered the first chiral molecule in space.
Amazing.
So you can look it up. I don't have details of it here in my slides, but that's sort of the holy grail of trying to figure out what went on. Look it up.
You made my day. Thank you.
Okay.
So you mentioned that there are several observations made from protostellar disks and stuff that were 10 billion years ago and stuff. So if they're so close to closer to the beginning of our galaxy, our universe than now, can we use those to make predictions that correspond to today's?
Sure. So let me clarify one thing, and that is that the thing that I showed that was 10 billion years ago is an entire galaxy that's very, very far away, and we're just receiving the light from it now. So we are not seeing individual stars form inside that galaxy. We're just seeing some kind of dynamical effect that's making the same chemistry happen. But there's a different way in which we use time to our advantage in astronomy, and that is when you look at different star-forming clouds, they're not all the same age. The types of processes that go on in astronomy are much, much longer than a human timescale. And so you can't watch an individual object go through all of those phases. But if you look at clouds that are different ages, you're essentially seeing snapshots at different phases in the lives of those objects. And so we use the large number of astronomical objects as a time machine when we're looking at nearby objects. I hope that.
Yeah.
I hope that.
One more? How you holding up?
I'm doing okay. My voice is getting a little shot, but that's all right.
Okay, so you spoke of the silicates and how they were aiding in the gravitational collapse along with water from which stars are born. I was just wondering, what do you think happens to those silicates after stars are formed?
So there are two places they can, or three places they can end up. They can end up in the star, in which case they're so hot that they're not silicates anymore. They can end up in the cores of planets like our Earth, which is mostly silicates, or they can end up incorporated into the cores of planets like the giant planets, which have a much higher ice content and an even higher hydrogen and helium content. They're still mixed in there. They're just a smaller fraction of the total mass of those objects. I'll take one more, and then we should go up the hill, right?
Yes, definitely. Anybody? Oh, yeah.
One more there.
Ah.
It's going to be a good one, too.
In our search for life out there, perhaps we need to temper that with our biased approach. We're looking for life as we know it.
Oh yeah, I agree. Yeah, and I want to be clear that when I say that the chemical conditions exist on other planets, I'm not a biologist, and I don't for any reason think that what's sitting in this room is the only endpoint of evolution, right? There are plenty of successful species on our planet that have been around much, much longer than we have. And finding brine shrimp in the oceans of a distant planet would probably be much harder than finding someone who's broadcasting TV signals. So I don't mean to imply for a minute that it will be easy to find or that it will look like us. Okay.
We want to thank you, Dr. Kaufman.
Thanks, everyone.